In this presentation, we will discuss the elimination method for solving systems of equations. Recall that a solution to a 2x2 system of linear equations is an ordered pair of the form x, y that satisfies both equations. For example, the point 2, 5 is a solution to the system with equations x plus y equals 7 and y equal 3x minus 1 because x equal 2 and y equal 5 satisfy both equations. We will first describe the elimination method by a series of steps and then illustrate the method with 4 different examples. First, we write both equations in standard form ax plus by equals c. Second, clear any fractions or decimals from the equations. Third, multiply one or both equations by a non-zero constant to create opposite coefficients for one of the variables. Then add the 2 equations from step 3 to eliminate one variable. Solve for the remaining variable. Then repeat this process to find the other variable. And finally, check the ordered pair in both original equations. Let's illustrate these steps with examples. First, let's solve the system with equations x plus y equal 2 and x minus y equals 6. We will apply the previous steps, but we notice the coefficients of y are already opposites, so we can add the 2 equations to eliminate y. Notice that adding the 2 equations is the same as adding equals to both sides of one equation. We get 2x plus 0y equals 8, thus x equals 4. Since x equals 4 and x plus y equal 2, we see that 4 plus y equals 2, so y is minus 2. Finally, the ordered pair 4 minus 2 checks in both original equations. For example 2, let's solve the system with equations 2x plus y equal 11 and x plus 3y equal 18. We notice that adding the equations now will not eliminate either variable. So we multiply the second equation by -2 and then add the equations. The first equation remains unchanged, but the second equation has been multiplied on both sides by -2. Now adding the equations eliminates the x terms, leaving minus 5y equal minus 25, so y equals 5. We still need to find the x-coordinate of our solution. So we start over with the original equations and multiply the first equation by -3 to eliminate the y terms. We get minus 6x minus 3y equals minus 33 and leave the second equation in its original form. Notice now that the y terms will be eliminated. Adding the 2 equations produces minus 5x equals minus 15, so that x equals 3. The ordered pair 3, 5 checks in both original equations. In our final 2 examples, we will consider the cases in which the system fails to have a unique solution. First, let's solve the system with equations 2x plus y equal 11 and minus 2x minus y equal 18. Notice that the equations already have opposite coefficients for x. We can add the equations in their original forms, and this produces 0x plus 0y equals 39. Hence, 0 equals 39. This is a contradiction, and therefore we conclude that the system has no solution. Finally, let's solve the system with equations 2x plus 3y equals 6 and minus 8x minus 12y equal minus 24. Our equations don't have opposite coefficients, so we need to multiply one equation by an appropriate constant. If we multiply the first equation by 4, then the x terms will have opposite coefficients. Our first equation becomes 8x plus 12y equal 24, and our second equation remains unchanged. But now when we add the equations, both x and y are eliminated, producing 0 equals 0. 0 equals 0 is an identity that is true for all values of x. Thus, every value of x will produce a solution to the system, and there are infinitely many solutions to the original system.